Hey, EP Statistics, welcome to part 2 of section 10.2. We're going to actually get into doing confidence intervals for mu1 minus mu2. The conditions for constructing a confidence interval, same as before, just kind of doubled. The data come from two independent random samples or from groups in a randomized experiment. If we're sampling without replacement, the 10% condition has to be met for both samples. And then our large count / normality, either for each sample, the population distribution needs to be normal, or the true distribution of response to treatment, as if we're doing experiment. So keep that in mind. Sample size is large and is greater than 30 for each sample. And if the population distribution has unknown shape and the sample size is small, we can graph the data and make sure it shows no strong skewness or outliers. But that would mean two different graphs, a graph for sample 1 and a graph for sample 2, or treatment 1 and treatment 2. All right, so checking conditions. A college student wants to compare the cost of 1- and 2-bedroom apartments near campus. She collects the following data on monthly rents in dollars for a random sample of 10 apartments of each type. So we got 10 1-bedroom apartments, 10 2-bedroom apartments. Let mu equal the true mean monthly rent of all 1-bedroom apartments near campus, and mean mu2 be all the 2-bedroom apartments. Check that the conditions for calculating a confidence interval for mu1 minus mu2 are met. So the first condition that we're going to want to look at is the random condition, and they did say that they got a random sample from each. So independent random samples of 1-bedroom apartments and 10 2-bedroom apartments near campus. So what would make these not independent is if you randomly selected 10 apartment complex, and then within each complex you checked a 1-bedroom and a 2-bedroom within that complex. Those would not be independent. Those would be related because they're kind of the data would be paired together, and we'll see what that looks like later on in the chapter. We'll deal with that. So it does need to be just a total random sample of one and a total random sample of the other, independent random samples. The next condition, the 10% condition. So both samples we're guessing are below 10% of all samples or of all apartments in the area. So there must, that's less than 10 is less than 10% of all the 1-bed apartments. 10 is less than all the 2-bedroom, 10% of all the 2-bedroom apartments. And then the normal, they don't tell us that are normal. We don't actually have large counts, so we actually have to graph our data. So the sample sizes are small, but the dot plots don't show any outliers or strong skew. So these are fine. 10 points is not great for making that assessment, but we'll go with it. All right, so then we're going to actually calculate our confidence interval, and this is going to follow the same format of statistic plus or minus critical value times standard deviation for statistic, or really on your formula sheet this will say standard error of statistic, and that is more accurate. Our statistic in this case is x bar 1 minus x bar 2. That's our statistic to estimate mu1 minus mu2. Our critical value is going to end up being t, but then we'll go standard deviation first. For that reason, we would like to use this formula, sigma 1 squared over, and so on and so forth. That's the actual standard deviation, but we're not going to know sigma. There's no reason we really should ever know sigma when we're trying to figure out what mu is. So, since we can't do that, we're going to have to use s instead. So the formula for the standard deviation, sigma are usually unknown, so we're going to use s instead. That makes this a standard error. And so since we're using standard error, we will use t instead. And so it will be, in the end, a formula looks like this: x bar 1 minus x bar 2 plus or minus t star times the s's in that standard deviation formula. So if the conditions are met, where t star is and this is new, the t star is the critical value with c% of the area between negative t star and positive t star for the t distribution with degrees of freedom using either option 1, technology, or option 2, the smaller of n1 minus 1 and n2 minus 2. So by option 1 technology, what that really means is there actually is a fancy formula. So usually we used to use sample size minus 1, if you guys remember, for degrees of freedom for our t, our critical t values and TCDF and so on. Well, with 2 samples, you got 2 different sample sizes. So the simple solution is you can go conservative and go with the smaller sample size minus 1. So pick the smaller. So if you have a sample of size 30 and a sample of size 40, you'd go with 29 for your degrees of freedom. That works, and that is conservative, but you can actually get a more accurate result by doing a combination of the two. But the formula is way too complex for us to like understand, and they don't put it on the formula sheet and so on. So let me show you that real quick. All right, so this formula right here is actually the degrees of freedom formula. Don't memorize it. Don't worry about it. But that's what somebody figured out is the actual most accurate degrees of freedom you can use for a 2-sample t confidence interval. So there it is. But you don't need to do that. The good news is your calculator will do this. When you do, and you go in your calculator, and I'll show you this again in a minute, but when you go into your calculator and you do the 2-sample t interval, let's see, 2-sample t interval, when you do this and you're going to type in a bunch of values here, it'll actually give you what that degrees of freedom is. It'll do it. And so that's what they say with technology. All right, so an example here. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, our researchers took a random samples of 30 trees from each half of and measured the diameter at breast height in centimeters. That's like across from the lowest branches. Here are a summary statistics and comparative box plots of the data. So we've got our 2 samples, our northern half 30, our southern half 30, and then the mean and standard deviations for each of those respectively, and a graph for each of those. So Part A, based on the graph and numerical summaries, write a few sentences comparing the sizes of longleaf pine trees in the 2 halves of the forest. So this is, just kind of going back to chapter 1. Be careful what they're asking for here. Just compare the sizes. So we want to compare shape, center, and spread. So the shapes, how do the shapes compare? Well, the shape distribution of DBH in northern sample appears to be skewed to the right. Well, most are pretty small, and there's a few really large ones. And while the distribution in DBH in the southern sample appears to be skewed to the left. So most up high, and then skewed to the left. And then outliers, no outliers are present in either sample. So that kind of work that into shape. The center, it appears that trees in the southern half of the forest have larger diameters. So south, we can see that both here in a higher median and in a higher mean. The mean and median diameter DBH for the southern sample are much larger than the corresponding values in the northern sample. Make sure when you're comparing shape, center, spread, you use comparative language like greater than, less than, more than, so on and so forth. There is more variability in the DBH in the northern longleaf pines. The range, IQR, and standard deviation are all larger for the northern sample. So we can see the range is a little bit bigger, and then we can look over here. We have this, IQR, the yellow block is bigger than the green block, and then the standard deviation is bigger for the north. So comparing shape, center, and spread. All right, now they want us to construct and interpret a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves of the Wade Tract Preserve. So our state, we're going to do a 90% confidence interval for mu1 minus mu2, where mu1 is the true mean DBH of all trees in the southern half of the forest. I don't know why they went with that first. I would have done north minus south just because that's the order they put them in. But I guess this will keep it positive, right? So south, since the southern ones seem to be bigger, this will keep the difference positive. So that might be one argument for it. But technically, you could do it either way if they don't specify. And whereas mu2 is the true DBH of all northern ones. All right, so plan, this is a 2-sample t interval for mu1 minus mu2. And you can get away with just saying 2-sample t interval. The mu1 minus mu2 is generally implied, but it's good to write that. The conditions, random. So we have independent random samples, 30 trees from each of the northern and southern halves of the forest. So we have both random. Both sample sizes are less than 10%, so that we'll have to assume there are at least 300 trees in each half. So 30 and 30 are both less than 10% of each half. And then the normal large counts. We don't know that they're normal, but our sample sizes are large. So central limit theorem gets them there. Both N1 and N2 are at least 30, just barely. So we're good to go. If we had to, if our sample sizes were smaller, we'd look at these and say, ooh, I don't know, that's pretty skewed, right? That would be kind of rough. The second one maybe not quite as bad, but still they're both kind of skewed, so we would have concerns about it if it was much smaller than 30. All right, so then the actual doing of this, we go ahead and get our summary statistics. We have X bar 1 and X bar 2, which now we're calling this one and this one too, and sample sizes. And you can also do it a couple of ways. So you can use the degrees of freedom using technology, which we'll do this on the calculator in a second, and it gives us this interval with that degrees of freedom, or we can do it by hand. So let me show you this with technology. All right, so we're going to go stat, tests, and then this is the 2-sample t-interval. 2-sample z-interval will almost never use. That would imply that you know sigma. In fact, if you click on it, it'll ask you for sigmas, which you don't know. So we're going to go to 2-sample t-interval, and we're going to input stats. If we had the raw data in list 1 and list 2, we could do that, and it actually speeds things up a little bit. But we've got raw statistics, and there's a good bit to enter. So we need X bar 1, which we were given as 34.53. That was the mean of the southern trees. The standard deviation of that group was 23.7. The sample size for that group was 30, and then move on to sample 2, and the mean was 23.7. Crap, I did that wrong. All right, so this standard deviation was not 23.7. It was 14.26. All right, so as I say, we didn't have the 23.7 twice. And then this standard deviation was 17.5. And this sample size was 30 as well. And then we're choosing a confidence level of 90%. And then it's going to ask this question, pooled or not. Our book doesn't really address this. Notice that, remember, we were pooled for a 2 proportion z-test. We pooled because the null hypothesis with the proportions are the same. Here, what this is asking about is actually pooling standard deviations. You can kind of group your standard deviations together if you have some reason to believe the standard deviations are the same. That's not really going to happen, and it's not really going to happen in this class. So you can just always leave that as no. If it asks this, the answer is no. Your calculator doesn't even ask when you do a 2 proportion z-test. It automatically pools because it knows it's supposed to. So this is asking if you want to pool standard deviation. So just note that one. All right. And then ultimately we get a degrees of freedom here of 55.72. And so that's actually a more accurate degrees of freedom for a 2-sample t-test. So you can use that one, and that's nice, is then you can use this confidence interval. So we're 90% confident that the difference is from 3.9 to 17.7. All right, so those numbers there, 3.9, 17.7. You could also have done this a little more by hand. So and remember, you can just do it this way on this test. Just make sure you do note the degrees of freedom. They want to see that when you do those things, what degrees of freedom you're using. You also could have done this by hand using the conservative degrees of freedom, which is the smaller of the 2 minus 1, which they're both the same, so it would have been 29. And if you do that, if you look it up in table B or you do inverse T, you can figure out that as you do inverse T of, in this instance is 90%, you would do 5%. So inverse T of 0.05 with 29 degrees of freedom, and you get that T star. And so you can plug that in, plug all this in, and get a confidence interval margin of error. And you get actually a different result. And this interval is wider than the one that we gave. Our interval was able to be narrower than this one. So ours went from not an insane amount, from I think it was 3.9 to 17.7. So we were able to shave off about a tenth doing it that way. Finally, the conclude step. So we are 90% confident that the interval from 3.9362 to 17.724 centimeters captures mu1 minus mu2, the difference in the true mean dBH of all the southern trees and the true mean dBH of all the northern trees. So on average, the southern trees are we're 90% sure it's somewhere between 3, where was the units? I don't know, I can't remember, centimeters or inches, anyways, whatever, units, from 3 to 17 units larger than the northern trees. So I kind of already showed you this real quick, but this is their summary of this. So for pooled, make sure you choose no for this, and you'll get that result. You can also do this with lists in your calculator. So you would have to have the data in L1 and L2. Make sure you set those frequencies to 1. We're not going to really ever need frequency data. And then same thing, it'll produce all the X bars and SXs and Ns and so on in the degrees of freedom, which is nice. It uses that accurate one. And I'll tend to use that accurate degrees of freedom. I won't use the conservative one because I prefer to use the calculator to do all that work for me, because I don't want to type that big formula in by hand. All right, and then a little AP exam tip. The formula for the two-sample t interval for mu1 and mu2 often leads to calculation errors by students. Also, the interval produced by technology is narrower than the one used in the conservative method. As a result, your teacher may recommend using the calculator's two-sample t interval feature to compute the confidence interval. So that's what I'm saying right now. Be sure to name the procedure two-sample t interval for mu1 minus mu2 in the plan step, and give the interval and the degrees of freedom in the do step. So when they grade these, I always want to know, they will either want to see the formula, which you could write, or you got to name it properly. So it puts a lot of emphasis on you being able to name. Our calculator says two-sample t int. Make sure you don't write that, write out two-sample t interval, and then even maybe for means or a difference of means, mu1 minus mu2. And then make sure you record the interval and the degrees of freedom in that case.